Started. Just let's make sure that this is recording. Is it recording? I think it is. Great, awesome. Let's get started. So at the beginning, since there have been many requests on this thing to do an example on the intermediate value theorem on how to justify. So we'll start with that and then continue with the material, unless you have some questions, but questions of the type, are we gonna have to do this, are we gonna have to do this, you'll see tomorrow, okay? So I'm not gonna answer those. If you have questions on the material, I'll happily answer them for like 5 minutes after this. So, show that, okay, f of x, let's see, let's pick something nice. Is equal to x to the 5 minus 16x minus 2. I mean, these are random numbers. Well, they're not random numbers, but has at least 2 distinct real roots. Okay. Great. So what is the root of a function? It's a solution to f of x is equal to 0, right? Yeah? Great. Now, here I have a polynomial, and I need to show that this has at least 2 distinct real roots. What do you have to do here? What's the theorem that comes to mind? Everyone? Intermediate value theorems. Very good. Great. So, what's the strategy here? What's the strategy here? Very good. Yep. You want this one out to say? Great. So that's what you have to find. You have to find values, or you have to find x values, so that f of x is positive and f of x is negative, and perhaps do that more than once, right? That's what you gotta do. Now, is evaluating this thing easy or hard? Evaluating a polynomial, is that easy or hard? Right? So, what's the first reflex? What's the easiest number to plug in?
0.
0. Let's plug in. What's f of 0? I mean, still, we haven't written anything yet, right? This is just for us. So f of 0, let me write this one here. F of 0 is what? F of 0 is minus 2. What's another one? Look, what's an easy number?
2.
F of 1. What's f of 1? F of 1 is 1 minus 16 minus 2, so it's minus 17, right? What's f of 2? What's f of 2? F of 1 is minus 16 minus 2 minus 18 plus 1 minus 17. Okay? Is that good? Yeah? Is that good? Yeah. What's f of 2? It's 2 to the 5, which is 32, minus 32 minus 2. So we're still minus 2. Great. So far, nothing, right? We can't conclude. What's f of 3? 3 to the 5 minus 48 minus 2. So it's 3 to the 5 minus 50. What's bigger, 3 to the 5 or 50? What's 3 to the 5? 3 to the 5 is 243, right? I mean, you don't need to know it. You just know that it's positive, right? F of 3. Okay, so what do we do here? We have at least one root. Now, if you plug in f of 4, do you expect the number to be positive or negative? Just for us to think. Positive, right? You get 4 to the 5 minus 64 minus 5. 4 to the 5 is much bigger. And so on. So looking for other integers may not be the best case, right? Great. So now, do we have a root or not? Does the intermediate value theorem guarantee us to have a root or not?
Yes.
Okay, so this root is let's give the best possible, well, not the best possible, but a nice interval would be between 2, 3. Okay, and now looking further, on positive integers is not useful because we know we'll get strictly positive values. Where do we look at now? Let's look at negative integers. We looked at 0, let's look at negative 1. What's f of negative 1? Who can help? Please raise your hands. Yes? 13. So 1 plus 16, minus 1 plus 16 minus 2. Thank you very much. We see this or not? So do we have at least 2 distinct roots? Are we good? Yes or no? Okay. So where are these 2 distinct roots located? There is one between minus 1 and 0, and one between 2 and 3. Now let's formulate our answer. What do we need? We need to formulate our answer correctly. So, what theorem I need to be using? The IVT. Great. So let's use the IVT. We have to justify properly. F is a continuous function. Well, let's not do that. F is defined and continuous on R. Since F, why is F continuous on R? Since F is a polynomial. Very good. Since F is a polynomial. Now, what is f of minus 1? 13, bigger than 0. What is f of 0? It's minus 2, negative. Okay? What is the other root? The other root is located between 2 and 3. What is f of 2? F of 2 is minus 2. And f of 3 is 3 to the 5 minus 50. Negative. 3, okay, I mean, you can compute it, or if it's obviously positive, you can just say that. Hence, by the intermediate value theorem, I don't want to see IVT. Just write the intermediate value theorem. Okay, it's not going to cost you 5 more hours. Okay, just by the intermediate value theorem, there exists x1 in what interval? Minus 1, 0, and x2 is equal to minus to 2, 3, such that f of x1 is 0 and f of x2 is 0. Hence, f of x has at least 2 distinct real roots. Okay, are we good here? This is how you should fully justify. Of course, you may, if such a question can appear, you may have something else as polynomial, right? You know, trig function, cosine x are continuous, inverse trig function are continuous wherever they're defined. Okay, so things like that you have to pay attention to. Always justify. Okay, if you just say f of minus 1 is 13, f of 0 is minus 2, so there is a root here, and f of 2 is minus 2, and f of 3 is positive, so you have a root here, you will lose, I think, as much as half the marks, okay? Because you should justify properly. Okay? Any questions? Great. Yes, sir?
For the exam, are we allowed to write like 3 to 5 minus 50? We don't have to evaluate it?
No, I mean, it's obvious, right? I mean, if it's obvious, it's obvious. If you tell me like 7 to the power 75 million minus 1, that's positive, right? Okay? already covered, but inverse trig themselves, we did some examples in class using inverse trig and intermediate value theorem, right? I'm pretty sure we did a few. Okay? Yes? A justification of?
Like an example of squeeze theorem.
Do you have an example? Because if I give an example now, I may be biased. So if you have an example,
No, I just wonder if you just.
yeah. Okay, so if you give me an example, I'll be happy to do it. Yes, sir.
Are related rates going to be on the exam?
No.
Like, can you do like x cubed sine x or something?
X cubed sine x. You don't, as x goes to.
So what would the justification require for a squeeze theorem?
It depends on the case, right? It depends on the case. So x cubed sine x as x goes to 0 doesn't require any squeeze theorem. You just plug in 0, right?
X goes to infinity.
That's infinite. That may not exist, right? Because sine x, you will, yeah, that may not exist. Okay? Because you will bound it, so let's see. You will bound between minus x cubed and x cubed, right? I mean, you cannot apply squeeze theorem.
Okay. Yeah.
Let's see. Yeah. I mean, you can show it doesn't exist by taking like subsequences, but that's fine. Let's not worry about this. Yes?
Could you do an example like arctan x minus sine x has a real root, right?
I mean, I have to think it through, right? I have to see it. But I mean, we have done examples in lectures. So okay, so please check the lectures. Great, awesome. Yes. Everybody. Yeah.
Could we do a problems plus unit 2 question 2 from it? Because I thought that was interesting.
What is it?
A problems plus question from the textbook. Could we do like question 2 from it?
What's problem?
Like the end of the chapter, like it's the practice question. I didn't get one of them.
Can I see?
Yeah. It's that one.
So find a and b such that the limit as square root a x plus b over x minus 2 is equal to 1. Yeah, I mean, what you have to do, you have to multiply by the conjugate, right? You have to put everything under you have to multiply by the conjugate. And first of all, what you can do is that it must be of the form 0 over 0. Anyways, okay, maybe I can explain that. Okay. Any questions? No more? Great. So we continue with the material. Last call for questions. Last call for questions. Again, I won't be doing any examples. If you have examples, you can tell me and I will do that. But I won't. Yes.
Is it possible to do like squeeze theorem without a trig function? I saw a couple examples of that.
Again, you have to give me an example. Okay. If you give me an example, I'll happily do it.
The limit of sine 1 over x as x approaches 0 doesn't exist.
That's right.
That
Doesn't
makes
it?
sense.
Yep.
But I have trouble with when it doesn't exist and when you can manipulate the function. Like I know that like there is obvious because like if you look on a graph it just oscillates.
Okay.
And also is it defined at that point? Like is it continuous?
So sine 1 over x is not defined as 0.
Okay, yeah.
So you cannot define it to be. You cannot define that function.
So it's not continuous.
No. So the question is that can you define f of 0 such that sine 1 over x, if x is different than 0, and f of is continuous, like with f of 0? And the answer is no, because the limit as x goes to 0, sine 1 over x doesn't exist.
Yeah.
Okay?
Yeah, makes sense.
Yeah.
Can we do an example of the squeeze theorem where you limit as x approaches 0 x times sine 1 over x, where the x is not x squared, so x squared is always positive?
Yeah. Okay. Okay. Sure. Let's do that. can do is that take the limit as x goes to 0 plus of x sine 1 over x, use squeeze theorem on that, and take the limit as x goes to 0 minus of x sine 1 over x, use squeeze theorem on that. Is that fine?
Yeah.
I mean, do you want, we can do it? Should we do it?
Okay.
Okay, great.
When you have sine of 1 over x over 1 over x, limit as x approaches infinity.
Yeah.
Is there a specific way we have to prove that, or can we just say that goes to 1?
So what is it? It's sine 1 over x is equal to 1.
Yeah.
Since the limit as x goes to infinity of 1 over x is 0, and the limit as t approaches 0 of sine t over t is equal to 1. Okay, this is how we just justify it. Any more questions? If you prove L'Hopital's rule, then yeah, you can. Yeah, sure. But I mean, we need a rigorous proof, right? We need a rigorous proof. And if the proof is wrong, everything else will be wrong. So, okay? I wouldn't. Personally, I wouldn't. So I can tell you, we'll make sure that L'Hopital's rule is going to be harder to apply. Okay? So that's one thing. So if you're going to apply L'Hopital's rule, you may be able to do it, but doing it with your lecture notes is easier. Just, okay? Great. Any more questions, or we should continue? Last call. Again, 1 more minute. Yes?
Can you show how to see if like an absolute value function is differentiable?
Do you have an example?
Like x, the absolute value of x minus 6.
The absolute value of x minus 6. Differentiable. Okay. What is that equal to? This is equal to x minus 6 if x is bigger or equal to 6, right? And is equal to 6 minus x. We agree with this or not? Everybody, do we agree with this? Absolute value of a is equal to a if a is non-negative, right? So if x minus 6 is non-negative, then the absolute value of x minus 6 is equal to x minus 6. And it's equal to minus x minus 6 if this is... Okay, so this function is differentiable everywhere except possibly at 6. So we gotta check that whether or not it's differentiable at 6. So what do? The limit as goes to 6 plus of f of x minus f of 6 over x minus 6. Okay, now if x is bigger than 6, then the absolute value of x minus 6 is x minus 6. Which is 1, right? Now, do the same as x goes to 6 minus. What do you get as an answer? Minus 1. Okay, so f. Let's write it down. The limit as x goes to 6 minus of f of x minus f of 6 over x minus 6 dot 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 is equal to minus 1. So, since 6 minus x and x minus 6 are polynomials, you repeat that?
The limit as x approaches 0 of t cubed over tan cubed of 2 times x.
T cubed over 2 times x.
Over tan cubed of 2x.
So you have t and x.
Yes. Or
It's either all t's or all x's.
2t. Tan cubed of 2t.
Oh, okay. So the limit as, you said x approaches 0 or t approaches 0? The limit of t approaches 0 of t cubed over tan to t, is that it?
Yeah, but tan is also cubed.
Tan is also cubed, that makes it easier. Great. Awesome. First thing to do, what do? What do? Plug in 0 over 0 and determinant form. Great. Now, what is tan? Tan is sine over cosine. Okay, let me rewrite this here. T goes to 0 of cosine cubed of 2t times t cubed over sine cubed of 2t. Okay, so far so good. Now, cosine cubed of 2t, where will this element go as t goes to 0? It will go to 1, right? Cosine cube of 0 is 1. So really the cosine here, it's better not to touch it, because that will just be 1. And this form, 0 over 0, is what will give you the indeterminate form. T cubed over sine cubed 2t. Okay? This is what will give you the indeterminate form. You agree? Yeah. Now, what do we have to use here? We have to use the sine x over x business as x goes to 0. But this time with x is equal to 2t. So let me, I have cos cubed of 2t times t cubed divided by sine cubed of 2t. Now, what's a good thing to do? What do I have in order to let sine x over x appear downstairs? Right? That's what you want, right? You agree? Sine x over x cubed. What is your x here? 2t. So you have to divide by 2t cubed. You agree or not? The top and the bottom. So let's do this. Cos cube of 2t times t cubed. And let's divide or multiply by 1 over 2t cubed. Divided by sine cubed 2t over 2t cubed. So far so good or not? Is that fine? Are we good here? Yep.
Could you re-explain why you just multiplied by 1 over 2t?
I need to apply sine x over x goes to 1. Right? So here as x goes to 0. So here I have sine x over x cubed. Right? So let's just rewrite this. As the limit as t goes to 0 of cosine cubed of 2t. Now, t cubed divided by 1 over 2t cubed, this will just be 1 over 8. 1 over 8 divided by sine 2t over 2t cubed. Now we have to justify. First of all, let's try to evaluate this. Cosine cubed 2t goes to 1, right? You just plug in. 1 over 8 stays 1 over 8. And this limit is equal to 1 cubed, right? So this is 1 times 1 over 8 divided by 1 cubed, which is 1 over 8. Since, always justify, since the limit as t approaches 0 of 2t is equal to 0, and the limit as x goes to 0 of sine x over x is equal to 1. Okay? Is that good? Okay, great. Yes?
Is there a specific trick? Like, how does the evolution
I listed them all. I listed all the ones that you should. Okay? Yes?
Sorry, the other one is,
Yeah. Oh, are you good with the board on the right?
yeah.
Okay. So t cubed. What is 2t cubed? It's 8t cubed. Okay? Yeah. Pardon me? Yep, please go ahead. Okay. What is the question asking? Show this? Okay, prove is equal to 0. The limit, sorry, would you repeat? Guys, please. Yes. Yeah. Okay. So this example, what does it involve? Everybody, what does it involve? Squeeze theorem. So the first thing we do, what's the first thing you do when you have a limit? You plug in. The first term, where does it go to? X to the 4 goes to 0. Everybody, are we all good with this? Now cosine 2 over x as x approaches 0. Does that limit exist? So the limit as x goes to 0 of cos 2 over x. Does this limit exist, or the function keeps oscillating quickly? The function keeps oscillating quickly. So can you apply the limit rule here? So you cannot apply the limit clause. Are we all good thus far? Yes. Okay. Now, what happens here? Who can help me start? In the back, yeah. Yep, minus 1, right? Minus 1 is this then. Yeah. So for all x different than 0, minus 1. Very good, you're attentive to this. 1. Great. Next step. In the back?
Multiply everything by x to the 4.
Yeah, and?
And then we have substitute the limit.
Wait, just why can you multiply everything by x to the 4? So you're saying multiply all the inequalities by x to the 4 and keep the order. Why are you able to do this?
Excuse me?
Why are you able to do this? This is correct, but why are you able to do this?
Like it's the inequalities, you can try to get the original functions that's in there.
Very good. Very good. I agree with you. But why are we able to do this? Why are we able to multiply by x to the 4? Sure. That's right. But there is, if you multiply everything by minus 1, does...
Oh yeah, you can multiply x to the 4. Well, and get squeeze here basically because when you substitute in 0.
Sure, but let's not worry about squeeze here. Let's worry about this step, which is good, right? You multiply everything by x to the 4, right? This is good step, but why are you able to do this?
Because x to the 4 is always positive.
Exactly. That's it. So since x to the 4 is strictly positive for x different than 0, you can multiply every term of the inequality by x to the 4 without switching the order.
You have to write the initial -1 is less than or equal to.
Yes, of course.
Okay, so you can't just get to the negative.
No. Yes.
What about if it was negative?
was minus x to the 4, you just have to flip them.
Yeah, I know you'd have to flip it, but if it's like 0, then like, oh wait, no, sorry, if it was x to the 3 or something.
You'd have to take some absolute values here.
Oh, okay.
Okay, you'd have to do something else. Yeah?
Can we go through an example with an odd number, 20 like now?
I mean, I think we'll just do this one and then, I mean, I think, yeah, okay, this is the last one, okay? I mean, I said maybe 10 minutes ago that this is the last example, this is the last question, and then we're gonna take, this is the last example we're gonna do, yes? I mean, okay, sorry. So if you have an odd power, just go to x0 plus, right, and do x0 minus, each on their own. I've answered this before. So if you have x sine x goes to over x, do the same thing. If x goes to 0 plus, you get 0. And if x goes to 0 minus, x is negative, so you do the same thing, but you reverse the equality, and you get 0. Okay? Yeah? Let's finish this one here. Great. Who can help now? Who can help? Yeah? And x to the 4, yeah, very good. The limit as x goes to 0. Of x to the 4 is equal to 0. Is equal to 0. What's important about these two things? Yeah, but it's not 0. Yeah, but exactly, that's the most important thing. So, the limit as x goes to 0 of x to the 4 is equal to the limit. Now, who can help me conclude? Who wants to finish this question? Who wants to finish this? Some new faces, some new voices. It's good to have new voices. Yeah.
Squeeze theorem. Whoa, sorry. Squeeze theorem says that if there's a function that is less than f of x for all x, and if there's a function greater than f of x for all x, then when the limit of the lesser function and the greater function are equal,
Yeah.
then f of x must be equal to the limit of those functions.
The limit, exactly.
So by the squeeze theorem, the limit as x to the fourth cosine of 2 over x as it goes to 0 is 0.
Awesome. Okay. Okay. Great. Now we have 20 more minutes, so I'll just save 2 more minutes after the 25, if you don't mind, just to finish this section. It's a small section. Okay, are we good with this or not? Yeah. Yes? Okay, is that clear? Awesome. Great. Let's continue with the, so I mean you have done like 90 minutes of review, which is, no, 50 and, I don't know, 50 and 35, which is not bad. Almost 90 minutes of review. So I hope it was helpful. Of course, we did not go through everything, but great. Now, let's do something easy. The tangent line approximation. Great. So, point of this. So suppose you have a differentiable function that you don't know how to compute, but you know how to compute the tangent line. This is A here. Okay? Now if x is close to A, if x is close to A, then f of x would approximately be equal to this, right? Look at the tangent line. Notice that if x is close to A, then the graph of f and the graph of the tangent line, they're a bit too close, right? You see this? They're a bit close. So the tangent line is a good approximation of f when x is close to A. Okay? And why is it called linearization? Because the tangent line is a line, right? That's a linear function. That's it. Okay? Let's do an example. Use the tangent line approximation. Oops, I shouldn't have erased that. Anyways. To estimate okay. Well, let's yeah, that's fine. Or 25.02. So I have to estimate square root of 25.02. Now, can you compute that using a calculator? Well, using your hands. Usually it's a bit difficult, right? I mean, it's not that bad, but it's a bit difficult, right? You agree? Square root of 25.02, you would need a calculator. Now, what do you not need a calculator for? Square root of 25. So, can you compute f of 25? What is f of 25? Is equal to 5. Now, is 25.02 close to 25? Yeah, it's a reasonable thing to say. Now, it may not be very close, but still reasonable. So, how do you approximate square root of 25.02? So really, what do you have to compute here? The tangent line at the point where x equals 25. What is that? So what is the tangent line in that case? The tangent line approximation. Y is equal to f prime of 25 times x minus 25 plus f of 25. Now what is f prime of x? If f of x is root x, what is f prime of x? 1 over 2 root x, right? What is f prime of 25? Is equal 1 over 10. Great. So, if x is near 25, f of x will approximately be equal to f prime of 25 times x minus 25 plus f of 25, right? This is just a tangent line. Nothing more. Which is approximately equal to 1 over 10 times x minus 25 plus 5. I just plugged in the number. I just found the equation of the tangent line. Great. Now, this is why I prefer to keep it in this form. So some people, this is why I like to start with the tangent line with f prime of a times x minus a plus f of a. Now, what is the value of x I'm looking for? What am I approximating here? I'm approximating f of 25.02. 25.02 minus 25, what is that? This is 2 over 100, right? This is 2 over 100 plus 5. Great, so this is 1 over 10. So this is 1 over 50. So this is 1 over 500 plus 5, which is 2501 over 5. Are we good here or not? Is that fine? What did I do? I just look at the tangent line. Instead of plugging in the x value in the function, I plugged it in the tangent line. Let's do one more. Use the tangent line approximation of f of x equal 1 over x to estimate one over 0.98. Okay. I mean, it's not bad. I mean, this is not bad to do, but let's try to do the tangent line approximation. Let's say around a suitable point. What's a suitable point here? What is close to 0.98 that is easy to find? 1 over, exactly. So the tangent line of f of x at x equal 1, really this is at the point where x equal 1. So what do you need? You need f prime of 1. What is f prime of x here? This is minus 1 over x squared. So what is the tangent line here? This is just f prime of 1 times x minus 1 plus f of 1. Right? You agree or not? Everybody? Do you agree? Now, this approximates f of x, provided that x is close to 1. If x is close to 1, I can approximate f of x by its tangent line at 1. Great, so what is f of x here? So f of x is approximate. So what do I need? I need f of what? F of 0.99 or 98 is approximately equal. What's f prime of 1? F prime of 1 is minus 1 times 0.98 minus 1 plus f of 1 is 1. So f of 0.98 is approximately equal to minus 0.98 minus 1. What is that equal to? This is also 2%, right? 2 over 100 minus 2 over 100. I mean, this is not plus 1. What do you get? Wait, what? Yeah, you get 98. Is that what you get?
It becomes positive because it's negative 1 times.
Oh, shoot, yes, thank you, thank you. You get 102 over 100, right? Or 51 over 50. Okay? Is that easy? Let's do one more. Approximate using the linear approximation. This is called a linear approximation of f of x equals sine x around a suitable point. Yes. Mind you, get this. This is f of 0.98. 1 over 0.98 is equal to f of 0.98. Right? This is f of x. So f of 0.98, this is equal to 1. Okay? F of x is approximately equal to the tangent line if x is close to. Okay? Now, if you want 1 over 0.98, what should you plug in for x? If you want 0.98, what do you have to plug in for x? 0.98. Okay? Great. So I have sine 59 degrees. What do you know about sine 59 degrees? Is it a remarkable angle? No. Is it close to a remarkable angle?
Yes.
It's close to 60 degrees, which is pi over 3. Right? So we use the tangent line approximation. Of f of x equals sine x around pi over 3. Since pi over 3 in radians is equal to 60 degrees. And I can compute the values of these things. Right? Now, what is a tangent line approximation? What is, if f of x is sine x, what is f prime of x? Very good, I think you should know this. F prime of x is cosine x. Now, if x is close to pi over 3, f of x is approximately equal to the equation of the tangent line. So f prime of pi over 3 times x minus pi over 3 plus f of pi over 3. So what's f prime of pi over 3? Cosine of pi over 3 is minus 1/2, right? Cosine of pi over 3 is minus 1/2. Sorry, it's 1/2, thank you. It's 1/2. Cosine of pi over 3 is 1/2. I don't know what happened. Plus sine of pi over 3 is root 3 over 2. You agree with this? Everybody, are we good? Great. Now, how should I plug x? Could I plug x as 59 degrees or I should transform it to radians?
Radians.
I should transform x to radians. What is 59 degrees? One degree is how many radians? Is pi over 180. So 59 degrees is 59 times pi over 180 radians. So sine 59 degrees is just equal to sine 59 pi over 180. Now, what approximation do I use here? I use the tangent line, right? Instead of plugging in x, 59 pi over 180 and sine x, which I cannot find, I plug it in the tangent line. This is approximately equal to what? To 1/2 times 59 pi over 180 minus pi over 3 plus root 3 over 2. This is 1/2. So this is 60 pi over 180. So this is minus pi over 180 plus root 3 over 2. And that's what you get. You get minus pi over 360 plus root 3 over 2. Okay, are we following what happened? Great, so what I want you to do is not to use a calculator. If you use this method here, you will be able to figure it out without a calculator by just canceling things out, okay? So on an exam, you won't need a calculator. Okay, so see you and good luck for tomorrow. Okay, bye-bye.